A major breakthrough in atomic science came in 1938 when Dr. Lisa Meitner and Professor Otto Hahn split the atom of uranium-238 in their laboratory in Germany. It would be 1942 before Enrico Fermi could demonstrate the possibilities of a self-sustained nuclear reaction in the United States. But before that happened, the nations of Europe were at war. The search for the secret of the atom's power was concentrated on the development of a bomb. When the war ended, the Navy and the newly established Atomic Energy Commission would then undertake what was to be a revolutionary project, the use of nuclear power to propel naval ships. In 1946, a group of naval officers and civilians were assigned to work on the Manhattan Engineer District's Daniels Tower Pile project at the Clinton Laboratories, now the Atomic Energy Commission's Oak Ridge National Laboratory, Oak Ridge, Tennessee. Senior member was Captain, later Vice Admiral, H.G. Rickover, a qualified submariner and engineer with a strong faith in both the practicality and necessity of atomic propulsion. His convictions and determination soon made him a dedicated and efficient spokesman for a nuclear navy. He became the driving force in the design, development, construction, and operation of nuclear propulsion systems for submarines and surface ships. The hopes of Captain Rickover and the Navy were encouraged when Chief of Naval Operations, Fleet Admiral Chester W. Nimitz, approved a program for the design and development of nuclear power. With the termination of the Oak Ridge Pile project, Captain Rickover and his group returned to work with the Atomic Energy Commission. Serving as the Director, Division of Naval Reactors, United States Atomic Energy Commission, and as Assistant Chief for Nuclear Propulsion, Bureau of Ships in the Department of the Navy, and with no precedent and no technology available for such an undertaking, he had to start from scratch. He had to conceive, design, develop a reactor in detail, and build and test the countless components and systems. Under his direction, the program brought in industrial participation. In 1948, the AEC contracted with the Westinghouse Electric Corporation for the development of a pressurized water reactor plant for the propulsion of a submarine. A land prototype of this reactor plant was constructed at the AEC's National Reactor Testing Station in Idaho. Construction began in August 1950, and the reactor was first operated at power on 31 May 1953. This was the first production of significant quantities of useful nuclear power in the world. The prototype was also used to train the crews which would operate the nuclear power plant. The nuclear navy needed highly trained and competent personnel to ensure the safe and proper operation of nuclear power plants. In 1951, the Navy awarded a contract to Westinghouse for the design and construction of a similar plant for installation in the world's first nuclear-powered submarine, the USS Nautilus. Design and development were done by the AEC's Bettis Atomic Power Laboratory in Pittsburgh, Pennsylvania. This laboratory is operated by Westinghouse for the Atomic Energy Commission. This is a simplified schematic drawing of a nuclear propulsion plant. This is the reactor, and this the steam propulsion machinery. The reactor, encased in heavy shielding, contains fuel elements of highly enriched uranium. Control rods of neutron-absorbing material control the activity of the reactor as they are inserted or withdrawn. As controlled fissioning or splitting of uranium atoms occurs in the reactor, tremendous heat results. This heat is carried to a steam generator by highly pressurized water. Here, the heat is transferred to less highly pressurized water, which is converted into steam to drive the ship's propulsion turbine and turbine generator sets. The turbine generator sets provide all the electricity required aboard the ship. This is the system that went into the Nautilus. The keel for Nautilus was laid at General Dynamics Electric Boat Division at Groton, Connecticut on 14 June 1952 by President Truman. She was christened by Mrs. Eisenhower on 21 January 1954. From the very initiation of the naval of nuclear power had been strongly supported by the Joint Congressional Committee on Atomic Energy. On 17 January 1955, Commander Eugene Wilkinson, first skipper of Nautilus, sent the triumphant message, "Underway on nuclear power." To the non-believers who had questioned the practicality and reliability of nuclear power, Nautilus soon gave answers that more than answered the questions. During her shakedown cruise in May 1955, Nautilus steamed submerged from New London, Connecticut to San Juan, Puerto Rico, a distance of more than 1,300 miles in 84 hours. This distance was 10 times greater than that previously traveled continuously submerged by a submarine. It was the first time that a combatant submarine had maintained such a high submerged speed, about 16 knots average, for longer than an hour. It was the longest period spent submerged by a U.S. submarine and the fastest passage between New London and San Juan by any submarine, surfaced or submerged. In 1958, with Commander William Anderson as captain, Nautilus spent 4 days under the Arctic ice, going from the Pacific to the Atlantic and passing directly under the North Pole. On her first charge of uranium fuel, Nautilus steamed 62,500 miles. More than half the distance was traveled fully submerged. For a conventional submarine of this size, more than 2 million gallons of fuel oil would have been required. Following Nautilus was Seawolf. The Seawolf's nuclear propulsion plant, which was cooled by liquid sodium, was designed, developed, and built by the Knowles Atomic Power Laboratory, Schenectady, New York, which the General Electric Company operates for the AEC. Seawolf first got reactor proved superior for naval applications, and further work on sodium-cooled reactors as a means for propelling naval ships was abandoned. So in 1960, her sodium plant was replaced by a plant similar to that installed in Nautilus. All subsequent naval nuclear propulsion plants have been of the pressurized water type. In the meantime, a more advanced and simplified reactor was developed by the Atomic Energy Commission. This plant, designated as the Submarine Fleet Reactor, was installed in the attack submarines Skate, Swordfish, Sargo, and Sea Dragon, and the missile-firing Halibut. Again, new records were written, new areas explored. Skate made the first transatlantic voyage to England and back while submerged. Later, she explored the polar seas. And in 1958, she went around the world in 50 minutes on a circular course 1 mile from the North Pole. Sargo spent 31 days under the ice cover exploring this almost uncharted sea. Sea Dragon was first to transit the Northwest Passage from the Atlantic to the Pacific in 1960. Skate and Sea Dragon met and carried out combined operations around the pole in 1962 and won the praise of President Kennedy for their conquest of inner space. They had shown that the icebound seas of the pole were accessible, that the Arctic could be used as an operational area for nuclear-powered submarines in all seasons. The USS Triton, one of the largest submarines ever built, 448 feet long, 7,700 tons. Triton added new records to the impressive list of achievements of nuclear-powered submarines. Skippered by then Commander Edward Beach, she made history in 1960 by circling the world underwater, 36,000 miles in 84 days. And at no time was Triton detected by our own or any other forces. Continuing advances in nuclear power plants combined with improvements in hull design and the development of a solid-fueled Polaris missile produced the dramatic and strategically potent Fleet Ballistic Missile Weapons System. Single-propeller submarines with higher speeds and improved handling characteristics carry 16 Polaris missiles capable of reaching any land-based target on Earth. George Washington in 1959 was the first. The others also bear the names of American patriots. Able to operate submerged for months, to cruise indefinitely at high sustained speeds, difficult to detect, they patrol the seas by day and night, the closest assurance to an ultimate deterrent in the world today. While the nuclear submarines were writing naval history with every voyage, a nuclear propulsion plant capable of propelling large surface ships was being developed by the AEC. A prototype of this plant was constructed at the National Reactor Testing Station near Idaho Falls, Idaho. And the Navy's first nuclear-powered surface ship, the cruiser Long Beach, which is powered by a modified version of the large ship reactor, was taking shape in the Bethlehem shipyard in Quincy, Massachusetts. In September 1961, Long Beach was commissioned. Possessing all the attributes of nuclear power, Long Beach can keep to the seas almost indefinitely and can operate at high sustained speeds far beyond the capability of conventional ships. Her naval tactical data system and other complex electronic equipment supply almost instant answers to complicated tactical problems. Conventional weapons and missile launchers give a powerful protective response in anti-air and anti-submarine operations. 2 months after the Long Beach was commissioned, the carrier Enterprise put to sea, nearly 86,000 tons, the largest and fastest warship in the world, with a flight deck covering 4.5 acres. Her 8 nuclear reactors produce in excess of 200,000 shaft horsepower to drive her across the seas of the world at speeds in excess of 30 knots. Because the Big E needs no fuel oil to run her reactors, she can carry extra aircraft fuel and ordnance to keep aircraft operating longer than similar fossil fuel carriers. As with all nuclear-powered surface ships, the absence of smokestacks and corrosive gases vastly decreases maintenance problems and permits the use of more effective fixed-array antennas. And flying conditions are improved by the freedom from smoke and hot gases across the deck. A wide range of armament, speed, and detection facilities make the nuclear carrier less vulnerable to attack. The third nuclear-powered surface ship, Bainbridge, a guided missile frigate, was commissioned in October 1962 and further demonstrated the advantage of nuclear propulsion for combatant surface ships. With her speed, endurance, and specialized weapons, she is well equipped for her task of providing a shield against enemy air or submarine attacks, or to operate efficiently on independent missions. In the early summer of 1964, Enterprise, Long Beach, and Bainbridge were deployed to the Mediterranean, assigned to the 6th Fleet to form the world's first nuclear-powered task force. On 31 July, the 3 ships were designated as Task Force 1, with orders to carry out Operation Sea Orbit. The cruise was to demonstrate the capability of these nuclear-powered ships to maintain high speeds for indefinite distances in all environments of weather and seas without refueling. Aircraft to people in remote areas of the world, to demonstrate the ability to reinforce U.S. power quickly in remote areas with a force ready to fight. To show the ships and their facilities to military and government leaders along the track of the orbit, distinguished guests from Africa, Asia, Australia, and South America were flown aboard on 16 different occasions. After they were given suitable honors, they were escorted around the ships. And later, on the reviewing stand, they saw a demonstration of some of the capabilities of the men and weapons of the Nuclear Task Force. The course of sea orbit followed around the coasts of Africa and up to Pakistan, south and east to Australia and New Zealand, continuing easterly along the Roaring Forties, around Cape Horn, up the coast of South America, and on to Norfolk. It was a track that passed through all the seasons, crossing the equator 4 times and coming within 500 miles of the Antarctic continent. From New Zealand to Cape Horn, more than 5,200 miles, the ships maintained a steady 26 knots, and there was plenty of power in reserve. The only import calls were in Pakistan, Australia and New Zealand, and Brazil. In each port, visiting was limited, but hundreds came aboard, and their response was tremendous. Task Force 1 proved its staying power and reliability, its freedom of action, and its complete independence of logistic support. These ships have increased the Navy's mobility, versatility, and effectiveness in protecting the nation's interests. They demonstrated on the long cruise their unlimited range, higher sustained speed, immediacy of response, and reduced vulnerability. When the ships came into port at the journey's end, they had covered more than 30,000 miles in 58 days at sea without replenishment of any kind, and without a single nuclear power problem in any ship, in spite of the rugged demands that had been made on them. Well, it's a long way from these scratches on a microphotograph to a task force circumnavigating the world, but the atom has made it. In the decades since Nautilus first got underway, the Navy's nuclear-powered ships have steamed more than 8 million miles. In all this time, no nuclear-powered ship has ever failed to meet an operational commitment due to a malfunction of the nuclear propulsion plant. With conventionally fueled ships, mobility depends mainly on fuel supplies. Even in peacetime, a worldwide fuel distribution is required to maintain our sea power. And in wartime, there must be an availability of oil stocks, storage facilities, tankers, and escorts to protect them. Protection is even more necessary during the actual period of replenishment. In heavy weather, refueling is often impossible. At times, this has caused destroyers to turn back for lack of fuel. And sometimes an entire force can be immobilized by an attack on the relatively vulnerable fuel train. But when task forces are nuclear-powered, fuel restrictions are ended. The full potential of logistic freedom can be realized. There is no longer a need for fuel availability or for establishing petroleum facilities, which has always been a major consideration in setting up advanced bases. In remote areas, the superior mobility of nuclear-powered ships may mean getting to a hot spot quickly enough to prevent a major eruption. The advantages of nuclear propulsion for surface ships were further conclusively demonstrated when the Enterprise and the Bainbridge joined the 7th Fleet off Vietnam on 2 December 1965. Marking the first time that nuclear-powered ships entered combat. During the transit from Norfolk, Virginia to Subic Bay in the Philippine Islands, the two ships maintained a speed of advance in excess of 20 knots for the entire 16,000-mile trip, despite the fact that flight operations were conducted for 9 days and 3 nights, arriving with sufficient jet fuel remaining to conduct days of heavy combat operations. The Enterprise, on her second day of operations, demonstrated her high state of readiness following this long transit by setting a new daily record for combat sorties by any aircraft carrier performing in-country support. The capacity for virtually unlimited steaming at high speeds means that hostile areas can be transited quickly. Submarine contacts or heavy storms are more easily avoided. Fast retirement can be made from the threat of air attacks. The element of surprise is increased, especially with the elimination of telltale oilers. The absence of smokestacks and air intakes makes it possible for nuclear ships to be buttoned up and washed down automatically in the event of atomic, biological, or chemical attack. The tremendous reservoir of power in the nuclear reactors is able to meet the constantly increasing electrical demands of communications, radar, sonar, and the naval tactical data systems, as well as the new weapons systems and the requirements of flight deck catapults. Another benefit of nuclear power is greater maneuverability. Instant power, power to move ahead, stop, or back up quickly. Among other advantages, this immediate response minimizes the exposure of with the cooperation of American industry have been spectacular. But we are still just on the threshold of a nuclear age. Knowledge, reacting to continuing nuclear discoveries, acts as a catalyst in many areas. It is reflected in power plants to produce electricity and to provide fresh water, such as this Navy installation at McMurdo Sound in the Antarctic. It stimulates medical and scientific research. At the National Naval Medical Center, Bethesda, special facilities and equipment are dedicated exclusively to nuclear medicine. Here, the Navy trains its own doctors, nurses, and corpsmen in the most advanced techniques. At the present time, we lead the world in nuclear propulsion knowledge. We have proven the superiority of nuclear-powered ships. Out of the unseeable atom, scientists and engineers of the Navy and the Atomic Energy Commission, working with leading industries, have developed and demonstrated the greatest power the world has ever known. What has been achieved is a monument to the men of vision who set their minds and hands to the almost insurmountable problem of isolating and controlling this prime force. They have made the submarine a true submersible. They have created the Polaris missile system as the most potent deterrent to enemy attack. They have opened the frozen seas of the Arctic. They have harnessed the unseen to turn the propellers of ships that can circle the globe without logistic support. And now they are developing higher-powered, longer-core life reactors for submarines and surface ships. 2 reactors, each producing about as much power as 4 of the Enterprise reactors, and with fuel lasting for approximately 13 years of normal ship operation, will propel the next generation of aircraft carriers to be constructed. New horizons are being revealed in medical and biological sciences. The way is being shown to new processes for industry. These men of vision have brought into being the vanguard ships of the nuclear navy, a vital force for the future, underway on nuclear power.